It's still muted. There's no audio coming through. Are we good? Let's just keep saying stuff, and then hopefully we get audio eventually. Okay, now we're good. Great. Thank you so much. I'll do that introduction again. As C Sharp Fritz said, my name is sadmoody. Well, that's my handle. My real name is Mahmoud Hikmet, and the reason I'm called sadmoody, and that's a thing that comes up a lot, is that when I was 11, like a normal 11-year-old child, I wanted to play Hearts on the MSN Gaming Zone because that was a thing. And I wanted to use my nickname, Moody, because everyone has trouble saying Mahmoud. So I go by Moody. It's what my friends call me. So I wrote in Moody, but the name Moody was taken. So I went with, and Sad Moody was the only option that didn't have numbers on the end of it. So for the last 20 years, I've been Sad Moody. It has nothing to do with my emotions or anything like that. I would have gone with Dr. Moody, but I was 11. I did not have a PhD then, so it wouldn't have worked. Okay, so let's get started with this. I'm from a company called Omeo. I'm the head of research and development there. We're a New Zealand-based company that is centered around making autonomous shuttles. And to learn a little bit about where we come from and what we're doing, I want to dig in a little bit into how we came about. So to understand Omeo, you need to understand the company we spun out of. It was called HMI Technologies. HMI Technologies makes electronic signs and road infrastructure. So LED signs that you see on the side of the road. We had some stints doing scoreboards. We still do as well. And in about 2015, we looked forward and said, things are going well with the electronic signs, but are we still going to be selling the same products 10 to 15 years from now? What are our products going to look like? And well, what do electronic signs do? Well, they're a medium of communication between the transport operator and the road user. And we're using LED lights on a board to communicate visually with people. They're a communication medium. However, as we go into the future and autonomous vehicles come about, will we still be communicating with them using lights on a panel? Our instinct was no, we probably won't. So let's actually, as engineers, get our hands on an autonomous vehicle and try to interface with it. So we started the first autonomous vehicle trial in New Zealand in Christchurch in conjunction with Christchurch Airport, a whole bunch of government organizations and some universities. And then Australia looked over at us, and Sydney and Melbourne, and said, we want trials too. So we started running trials from about late 2016, early 2017. And they were there just to give everyone understanding around autonomous vehicles. So that's how we sort of entered it. We said, let's find out about these things. So one of the first things we wanted to do was a practical application, which is let's connect an autonomous vehicle with a red traffic light. So we wanted the vehicle to stop when it got to a red light. So we approached the vehicle manufacturer and we said, we'd like to make your vehicle stop when it got to a red light. And they tell us what signal we need to send to it, or tell us how to interface with the API inside it in order to get the vehicle to pause its trajectory for a little bit. And they said, nope, you're not going to do that. We're not going to let you do that. The only way you'll be able to do that is if we decide to develop it, and then we will give it to you. And we thought, that's really bad. That's not the way things should be. And it seemed crazy to just sit around and wait for someone to develop something that stops when it got to a red traffic light. So we said, all right, let's just roll up our sleeves and make our own autonomous vehicle. So we did. In May 2017, we said, let's put aside the challenge of building a whole vehicle. Let's just take a golf cart and make it drive by itself. So we did that. It took us about 5 months, which is so fast. I'm so proud of the team for getting that far. And then by September of that year, we had the first autonomous vehicles running on New Zealand roads with these Omeo hops, these little 4-person vehicles, which was pretty cool. About a year and a half from getting to that stage, we actually delivered the first, I think, Southern Hemisphere produced commercial autonomous vehicle. It's a 20-seater, the Omeo Lift. It's the first one made in New Zealand. And it's also the world's largest 3D printed vehicle. So all the white parts that you see to it is just 3D printed. We had trouble finding a manufacturer that would build just a one-off. So we just 3D printed it in a 21 square meter 3D printer, assembled it in parts like a jigsaw, and we got it working. And now that vehicle is working in Christchurch Airport, the same place we started our first trial. And we can get it to do things like stop and change its trajectory and that sort of stuff. So that's been a really cool ride, actually. Pivoting from like an electronic sign company to coming to autonomous vehicles. Now, entering into autonomous vehicles, we need to get some terminology out of the way. So when people say autonomous vehicles, a lot of the time they mean different things. And there's actually these SAE, the Society of Automotive Engineers standard, that's centered around what level of autonomy a vehicle is. It starts with level 0, which is not autonomous, which sounds funny. It's like my 97 Toyota Corona is a level 0 autonomous vehicle. But that's like a completely human-controlled vehicle. When you get to level 1, you're talking about a vehicle that has some automated function. So you either get your hands off the wheels or your feet off the pedals. So something like cruise control would be level 1. Level 2 is when you can take both your hands and feet off the wheel at the same time. Hands and feet, off the wheel and pedals, both at the same time. So what Tesla is doing with their autonomous drive, that's level 2. It's not a vehicle that's expected to take you from one place to another place autonomously. It's a vehicle that's meant to work to do a pretty specific function autonomously by itself, but it still needs a human to oversee everything that's happening. Level 3 is a really scary level. That level is when the vehicle is mostly autonomous, except in safety situations where it doesn't quite know what to do. It throws all control back to the driver, and the driver decides what to do. That's really scary. I'm morally and technically opposed to level 3 ever existing. There's a whole bunch of research about supervised driving versus active driving and reaction speeds. So level 3 is a bit weird for me. Level 4 is when is the first one where you don't really need a steering wheel or pedals. So this is an autonomous vehicle that works in all expected environments. Now, what's expected? That's up to the manufacturer to decide. So some manufacturers would say, well, only this geo-fenced area is our expected environment, or only this track. That's where we're going. That's where we exist. So level 4, our vehicle works on an autonomous tram, like an autonomous tram on virtual tracks. It doesn't deviate off them. It's a much simpler problem than level 5 autonomy, which is like the holy grail of autonomous driving. That's a vehicle you get into, and it takes you from one place to another place, and you don't even need to look at the road or anything like that. Level 4, it might get into a situation where it's not sure what to do, so it knows how to pull over safely. Now, as the head of research and development, I'm usually tasked with technical direction and looking at where we're going in terms of a technical roadmap. But I'm finding that the big restrictor for autonomous vehicles aren't really technical problems. They're actually problems that are based around education, perception, and talking with people. And every time I try to talk to people about tech, I get presented with the same couple of words.
Self-driving cars and the trolley problem.
The trolley problem?
The trolley problem.
Trolley problem.
The trolley problem.
The trolley problem.
The trolley problem.
It's everywhere. The trolley problem, it comes up every time I try to talk with someone who's considering autonomous vehicles for the first time. Now, what is the trolley problem? There's a short video that I'll show you that explains it in very quick term. It comes out of the field of ethics.
Down this stretch of track, a runaway train is about to career. In its path are 5 unsuspecting people who will all die if the train hits them. But there's a switch. it will divert the train onto another track, saving the 5, but condemning one unsuspecting person to certain death. In essence, you have to decide, do you kill one person who's not in peril to save 5 who are?
It's like an ethical dilemma. There's no right or wrong answer. It's like there's no right or wrong answer. If you, do you intervene with a situation that where more people would have been killed in order to directly kill one person who wasn't really involved in the situation? There's no right answer, and you can go on and on about it. Everyone has a different interpretation for it. My favorite one is this one.
Nicholas, this train is going to crash into these 5 people. Should we move the train to go this way, or should we let it go that way? Which way should the train go?
This way. Uh-oh.
Look, it's open to interpretation. Everyone's got their own sense of morality, and we can discuss about the trolley problem and what it means to each person. It's a totally valid problem. It's actually been talked about so much that it's also a meme. You would have seen these around, and I think we can officially call the meme dead. It's now used as slides on a conference. So this is my attempt to kill the meme. But what does the trolley problem mean to autonomous vehicles? Since we're not talking about a runaway trolley on tracks, we're talking about an autonomous vehicle hurtling towards a group of people. So this is what that means.
Imagine you're driving down a country road and a whole gang of people jump out in front of your car. There's an escaped convict, a toddler, a mother with a baby, a 95-year-old war veteran, and a small kitten called Pickle. You can't brake or swerve, and you're going to kill one of them. Which do you pick?
So the problem is always centered around, you're going to kill either this group or this group of people. Who should the autonomous vehicle kill? Oh no, these companies are so terrible and evil, they're deciding in code who to kill. I can tell you from a technical point of view, this is absolutely ridiculous, and it's not something that's even considered or is worth spending your time on. And that's what I'll spend a little bit of this talk discussing. But like this notion of the autonomous trolley problem is everywhere. Even MIT tried to crowdsource morality by creating this thing called the moral machine, where given a scenario and the vehicle decides who to kill in a situation, they sort of get a gauge as to what society thinks is the right or less wrong thing to do in a situation like this. So in this one, it's like a group of women, one is pregnant, they have the right to cross the road, and in this is a group of men, one's homeless, one's a burglar, and they're not allowed to cross the road. Which one do you do? There's all sorts of these. If you just search up MIT moral machine, you'll be able to participate in this. But anyway, to understand why the trolley problem doesn't make sense, we first need to answer, how does an autonomous vehicle move? So let's take like a couple steps back and think of things in really simple terms. When I was at school, I had these devices. They're called ladybugs in some places. In other places, they're called, I think they're called turtle bots. Basically, they're little programmable robots that children can basically say, go forward 1 step, turn right 90 degrees, etc. And you can put a pencil in this like little, or a felt tip pen in this little hole, and it ends up drawing the picture that you programmed. This was one of my first interactions with programming, and I remember it really fondly. But if you say you have this, and you write a quick program for it that's sort of move forward a step, rotate 90 degrees clockwise, someone who maybe has a little bit of visual, can look at things a bit visually, will be able to read that and sort of ascertain what the path is going to be. But the vehicle sort of goes through, it executes each instruction, and it does it, and eventually you end up with the pattern that you decided to draw. In this one, I drew a number 7. I don't know why. I think I picked things randomly and it came out that way. But by looking at just this code without needing the robot to actually do it, you could have predicted that the vehicle or this robot would end up in this place and it would take this path going around by just following these steps. You've got actuators, which are based around steering. Actuators, you can think of them as motors. You've got actuators which go with steering, and actuators that go about moving forward or moving back. We can do the same thing with a vehicle. So if we've got 6 or 7 inputs that are coming forward into the vehicle about the acceleration and the steering angle that's going to be for the wheels, for the steering wheel, you can see what the path of the vehicle is going to be. So with that, we've got a sort of model that allows us to predict or sort of simulate what's going to happen to the vehicle as it goes through. So, how does an autonomous vehicle make decisions? Well, there's a lot of different ways to program an autonomous vehicle, and there's lots of different thoughts around it. On one end is explicit, and by explicit programming, I don't mean like programming with swear words in it. I mean like you're explicitly defining each step of the way, what the vehicle does in certain situations. On the other side is data-driven. So rather than explicitly telling the vehicle what it should do in certain situations, you say, here's a bunch of data about how to drive, and the vehicle learns from that. And eventually you get generalized behavior. So the good thing about explicit programming is that it's easy to update or change predictably. If a vehicle does something you don't want it to do, you just program that edge case out from there. However, if it's presented with a new situation that you haven't accounted for as a programmer, you might get some unpredictable behavior. But basically, the programmer decides what happens in each behavior, in each situation. With the data-driven side, you can't really update or change it predictably. The model that you get is as good as the data that you present it. So it might be biased in one way or another way. It probably succeeds in new situations. So it's a data-driven way of programming is really good at generalizing what you want it to do. So when presented with a situation it's never seen before, it relies on the rules and the data that it's modeled itself after to behave in that way. And the data decides on behavior. The bad thing with each of these is that if you explicitly code something, you're not sure how to deal with edge cases. With data-driven ways, you might get emergent behavior that is that you don't like. So emergent, because you're not telling the vehicle exactly what to do, it might decide to just turn left really poorly. The way you fix that is by throwing more data at it, and hopefully that gets learned out or unlearned. But by doing that, you're changing the model entirely, and so the vehicle stops acting exactly the way it was before. So it can feel like a bit of a game of whack-a-mole. Our approach, as always, is somewhere down the middle with something called model predictive control. What is that? It sounds complicated. It's not. I'll go into it very easily. So we create a model of the vehicle in software, very similarly to what I showed before. Like you've got a vehicle, you know what the vehicle goes through given actuator inputs. So we can change what inputs are, and we see what the output of those, what the state of the vehicle is going to be. We do this lots and lots of different times with lots of different types of actuator inputs, and we try to find the best one. But how do you find the best outcome becomes the next question. So how does an autonomous vehicle know the best outcome? Well, in terms of optimization, and this is an optimization problem, you don't necessarily go for the best outcome, but you go with the least worst. And that all makes sense as to why in this next slide. The reason we call it the least worst is because we give something called cost to the model. So we have a cost function, and we tell it the things that we don't like, and we assign costs to those. So we say, if you hit something that costs a lot, you shouldn't stay still. If you stay still, that costs you. What unit does it cost? It's just a number. So you can think of them as like bad points or money if you don't like spending money. So you don't go faster than the speed limit. You up the cost the higher you are from the speed limit. Yeah, don't stray from the track. Don't turn at high speeds. So we can let the vehicle decide the least worst outcome based on the cost function that we give it. If we find it doing something bad, we just introduce a new cost attribute, or we just append that cost function to have a cost associated with that bad action. And the emergent behavior should be that it doesn't do that thing anymore. So we can change the behavior of the vehicle based on what we tell it's important. So we're literally programming the values and how important certain things are to the vehicle against each other. Now, how does an optimizer work? You can think of it really simply as, say you have a cost function, which is y equals x squared, which is just this parabola, and your job is to guess where the lowest point on this is, so the place with the least cost. You don't know what the shape of the graph is, so I'm sort of showing you behind the scenes here, but don't tell anyone. But what we do is we make a guess. We make an initial guess, and in this case we guess 10, and our cost here is 100. That could be okay, but we can keep making guesses. So our next guess would be 5, and we see that we get 25. Okay, we're heading in the right direction. Next, we guess like 2, and we get 4. That's really good. See if we can get down to 0, and maybe we go a little bit further, and then we know that we're heading in the wrong direction, and you sort of iteratively find the local minimum. You might not find the global minimum for the whole thing, for the whole state space, and that state space is going to be really complicated for a very complex problem, but you're trying to find the least worst solution that is within reach. And from the perspective of the optimizer, this is what the cost function looks like. So what do we do inside our cost function? Well, we have different orders of magnitude. So the highest, the most important things cost the most, and the least important things cost the least. So the things that cost the most are obstacle avoidance. So if you hit something, that is the worst possible failure for a vehicle manufacturer, to an autonomous vehicle manufacturer to go through. It should avoid obstacles at all costs. Next step down. So by orders of magnitude, I mean that this might cost like 100,000, and then this might cost 1,000 to 10,000 in terms of bad points that we were talking about before. Mission goals would be things like, where are you going? Are you on the track? Are you going the right speed? And then all the way down the bottom would be comfort. Are you accelerating really quickly, decelerating really quickly, steering too heavily? The reason we separate things by orders of magnitude is because we don't want the vehicle to go, well, yeah, unfortunately I did run over a person, but at least I didn't brake heavily. So you need to sort of give it a, it needs to know the order of magnitude of the different parts. So what does a cost function look like from the perspective of a vehicle? Well, we can sort of map it out. And this is a really simple view of what it looks like. So there's this sort of horseshoe-shaped track. The bottom of the valley is the least amount of cost associated with it. So you can imagine yourself sort of running down the bottom of a valley, and someone's telling you, look, you can't go above a certain altitude. If you do that, you need to stop running. There's no oxygen above there. And so you know that you just need to keep running along, and your path might end up looking something like that, because that's the path where everything is dark blue and it's okay. Now, if someone gets in the way, this is what the cost function looks like. So, so veering off the track is pretty bad, but hitting someone is way, way, way worse. And so your cost function, your trajectory ends up looking like this, where the vehicle ends up stopping if something gets in the way, because if it goes around these, it would have veered off the track for far too much for it to be okay for it to run. So the vehicle would just put on the brake. So looking closely, this is two different people. One might be more important than the other. And on my streams, we joke about having one be a baby, one be a grandma. So regardless of which one is more important than the other, the order of magnitude of hitting something bad is so bad that it doesn't even compare to the rest of the track. And so you end up just braking. It just breaks. it's a really unattractive answer. It's a boring answer to what sounds like a very interesting problem. And look, we even coded it. I coded this live on stream, and we had a vehicle that we built this completely from scratch. And when going against a granny or a baby Yoda, it just sort of breaks, and that's all it does. We played around with it as well. We changed the costs to a negative number, so the vehicle started to like go out of its way to like run over baby Yodas and grandmas. So it became like a death machine, which was fun. Not showing that clip here. Far too violent for this conference where we're supposed to be all good and PG. So someone's clipped that. I'm sure if you're wanting to look for it, you can find it. So, how does an autonomous vehicle find itself in the trolley problem? What is the premise for it? Well, I've boiled the the trolley problem down to this very basic statement, which is a self-driving vehicle is driving down a road when suddenly two people, a baby and a grandma, enter the path of the vehicle. The vehicle brakes do not work. If the vehicle continues, it will kill both of them, should the vehicle swerve to hit the grandma or the baby. And that's just a very basic trolley problem. Let's investigate what is wrong with this, now that you know how things work. So a self-driving vehicle is driving down a road when suddenly, so the first problem is suddenly, like the sudden appearance. How did people just arrive suddenly in front of the vehicle? A vehicle's equipped with all sorts of sensors, LiDARs, radars, cameras, ultrasonic. It's highly improbable that one or two people are not detected by the vehicle until too late. So it'll be driving slowly or not at all if it's unsure of its environment. And moving objects can be detected and their trajectories can be mapped. So you would need to react to the potential paths, not the actual path, but the potential paths of the obstacles around you, and that's what you avoid going into the future, and you react accordingly. So the vehicle would need to be traveling at a high speed on a one-way street with occlusions on both sides, with both the baby and the grandma being very well synchronized and jumping out from behind obstacles. But assuming that that's happened, assuming we've got like a in-sync baby grandma death team. So let's keep going. It's suddenly two people, a baby and a grandma. Who's in the way? So a human would be able to say one's a baby, one's a grandma. But now there's two objects are in front of the vehicle at the last possible second. The vehicle... So... The vehicle needs to be capable of identifying the objects as people. Once identified as people, the vehicle needs to discern their age accurately. So it's not just about recognizing them as people, but figuring out what their ages are. So to do that, you'd need to build some sort of algorithm, some computer vision algorithm that can see what is the age of the people in front of me. And you're penalizing age, not bad skin or posture. And you need to be sure that that baby on the road is a baby, not a doll. There's a lot of problems. There's a lot of problems around this. And so what you need to, and like, it's not about just getting the latest computer vision algorithm or something like that and just letting that run, because you need things to run at a safety critical level. And a safety critical level is like a much higher barrier that you need to pass. These need to run reliably. You're literally choosing who dies. So it's not about getting 30-40% accuracy for a toy on a computer, like on a phone. You're actually making a decision about the death of someone. This is a really complex problem that I'm not aware of being solved yet. But okay, let's assume that we've solved this problem. Let's carry on. So the baby and a grandma enter the path of the vehicle. The vehicle brakes don't work. Why don't the brakes work? So the brakes don't work for some reason. It's always given as a thing that's just happened. A vehicle has onboard sensors which actively check on the status of all the vehicle systems. So if the brakes don't work, the vehicle shouldn't start. It'll be much better with autonomous vehicles than it is for the vehicles today. But okay, let's keep going. If the vehicle continues, it'll kill both of them. Should the vehicle swerve to hit the baby or the grandma? Swerving, that's a huge problem. So autonomous vehicle engaging in a Hail Mary maneuver, you should be minimizing the harm. However, swerving is a chaotic behavior that's incredibly hard to model. You need to know if there are rocks in the way. You need to know if it's rained recently, if there's paint on the road, what's the coefficient of friction in front of you, what are the treads like on the tires. It's a really complex dynamic mechanical equation, which is prone to chaos. So, like, what's the weight distribution? All of that changes what happens in that situation. So, but yeah, all right, you can assume that that's done. But I mean, there's so many problems. I mean, here there's 4 extremely hypothetical hypotheticals. Like, if they suddenly appear, if you can detect both of them, if the brakes aren't working, if you can work out how to swerve. It's so many ifs, hypotheticals on hypotheticals, when it just breaks. Like, that's all that happens. The vehicle just breaks. But, okay. So, we know that the trolley problem isn't something that makes sense. But why is it so popular? Like, I need to understand where it's coming from. Because I need to be able to answer these people that constantly ask these. And these people aren't just, like these people are regulators. There's some technical people. There's also some not so technical people. And they vary. But I need to understand what their motivations are for asking a question. But writing questions about something where the vehicle decides who to kill in a situation gets you headlines looking like this. And headlines looking like this have words that look like this. And these give you a lot of these. And a lot of clicks equals a lot of money a lot of the time. But it's unfair for me to just say that that a sensationalist way to write is the only way, to get money for clicks is the only reason that these sort of these questions exist, because that's not the reason. I mean, I've explained to you very simply how a vehicle moves, how an autonomous vehicle works. It's unlikely that anyone has ever taken the time to do that in the past. It's always been the vehicle is Skynet, or the vehicle is able to do whatever it wants in this situation. So, I mean, model predictive control, if you go to the Wikipedia page, this is how it's described. So if someone tells you, our vehicle uses model predictive control, or it uses convolutional neural networks, or whatever algorithm someone chooses, if someone who's non-technical goes and searches for it, this is the sort of information that they need to dig through. Now, weird flex, but okay, I've got a PhD and I have trouble understanding some of this stuff sometimes. So if I have trouble with that, what's someone who has no scientific background like? So what it comes down to, in my opinion, is science communication or miscommunication. We're not explaining things, we're not talking about technology in a way that makes sense to non-technical people. The way we communicate technology is not accessible to most people. And this gives you a couple of problems. Either you overpromise or oversimplify something, where you say, trust in this technology, it'll solve everything. Or you make it seem so complicated that the person can't even understand it. Each of these leads to different outcomes. One is inevitable disappointment with the technology and a lack of trust in what you can do in the future. If you say, we can solve all our problems using blockchain, for example, and someone implements that and it doesn't work, they're not going to trust you anymore going forward. Their likelihood to adopt new technology is compromised. And if someone doesn't understand something, or you make it overcomplicated, it might make them scared, or it might make them so bored that they won't care about what it is you're talking about. So there's far too much time and effort, especially in the field of autonomous vehicles, being spent answering or mitigating the wrong problems because they're seen as critical or important. And the big thing around this is that decisions about technology will still be made even if the decision makers don't understand the technology. Like if you have a minister for transport that doesn't come from a technical background and they don't understand what you're working on, they're still going to make legislative or regulative legislation or regulation that outline what you can and can't do. And look, no decision's also a decision. So a lot of times you can talk about all the uncertainties around the technology, but making no decision is a decision. So for a regulator, for example, not making a decision because there's nothing out there yet, not creating a framework for a market to bring itself out in, means that you're leaving it to the private industry to determine what that market looks like, how it operates, who profits from it, who it ultimately serves. So that's really where it comes down to, and the problem that I find that underlines the trolley problem. But now, I don't want to leave you without discussing whether there's an actual trolley problem, because there are. There's actual trolley problems around autonomous vehicles. And here's one that I've thought of. So 94% of road accidents are a direct result of human error. On a pie chart that looks like this. So the green ones are the human error. So that last 6% is things like car breaking down, etc. So autonomous vehicles will still cause road deaths. No one is saying that they're going to stop every death that happens on the road, but they'll keep getting safer. The more you wait, it's the law of, the law of incremental, sort of diminishing returns. Every year you get incrementally less and less and less better, approaching 100% safety, but never quite getting there. They're going to keep getting safer. The more you wait, the safer they'll get. So you're a regulator. There's 400 people dying on New Zealand roads per year. In the US, it's 40,000. So one person a day dies in New Zealand, 100 people a day die in the US. Introducing autonomous vehicles would lower that number considerably. However, the remaining deaths will be directly caused by autonomous vehicles that you introduced as a regulator. Would you pull that lever? That, to me, is a trolley problem. Thank you. Cheers. Do we have any questions? That was my talk. Welcome. Thank you for coming to my TED Talk, guys. Sadmoody, how do you really feel about the trolley problem? Trezzy. Look, the actual trolley problem is fine. It's something that we can discuss, and it goes into like the purpose of the actual trolley problem as the ethics, like the philosophical ethics problem. That's a great thing and a fantastic exercise to go through. But then when you try to fit it around into like the autonomous vehicle deciding who to kill in a last minute scenario, that makes people discuss far too much about things that don't even really impact autonomous vehicles. So I can tell you that because people think that the trolley problem, as I presented it before, is real for autonomous vehicles, that's holding back the rollout of vehicles, which could lead to lower road toll. And by road toll, I mean deaths on the road. So, it's dangerous to have these sorts of ideas and these discussions that hold back technology. But thanks. Code Alpha. So should we be building flying self-driving cars? There are actually companies out there who are looking at the flying problems. And while you kind of do have those almost, like a plane would technically be what, a level 3 or a level 4 autonomous vehicle. It can go in autopilot for the majority of the time. I'd say, yeah, a plane would be like a level 3 autonomous vehicle. But like getting into consumer planes, that's for autonomous driving, I still think that's a way off. Lily Hazel, do we have slides for this presentation? I've got slides. I'd be happy to share them if someone would like. I understand that this is all being recorded, so there'll be VODs out there. If you want me talking, if you want to just plagiarize this, you're welcome to. Just let me know. It'll be, yeah. I like knowing when people are using the things I create. So thanks. Next, Zanian's asking, I like that there's no middle ground, like no expectation that the AI performs at least as well as a reasonable human actor. It either has to be perfect or it's useless. Exactly, Zanian. There's some really interesting new applications and things that come out. So for example, the way that a driver now works, a human driver on the road, each of us need to learn from scratch how to drive a car. So a lot of us will be making the same problems. Like you might go into a blind corner way too fast and get into a near miss. Some people will get into accidents and die, but the ones who had near misses, next time they're going around that blind corner, they're going to take their time. That is, with autonomous vehicles, you can take the lessons that one vehicle in the fleet is learning. So yeah, it won't be perfect. It'll get into a situation that is probably bad. There might be people that die, but the data that you get from that situation allows you to make the entire fleet react as if they had learnt that lesson themselves. So we sort of learn at a much faster pace, and we can approach a perfect fleet as fast as possible. We can continue to. You'll never get perfect. I mean, like, if someone wants to jump out in front of a car and actually harm themselves, that's not going to stop. Autonomous vehicle, there's the laws of physics. They're going to get in the way, but we can at least do our best to collectively learn from all the different sensors and data points that we have around. OJ Pete asks, is that communication of technologies isn't accessible to most people, or is it that people are too lazy and happily ignorant to try to understand what's being said? It's a mixture of both. So from the perspective of people, I found that people respond the best to narrative and emotion. So as a communicator, as a technically based communicator, I had to learn how to create stories when I'm talking about things, and how to target emotional trigger points with people when talking about things, because otherwise it's just a technical talk, and if someone is not hyped about the technology you're talking about, they're not going to care about what you have to say. From the point of someone who's technically minded, a technically minded person will be very careful on not misrepresenting something. However, by trying to be 100% accurate in everything that you're saying, then you end up overcomplicating the models and analogies that you're using. It's much better, in my opinion, when you're communicating with a wide audience, or you know that you're going to be communicating with a wide audience, is to simplify things enough so that they might get a flawed understanding of it, but they understand the gist and the consequences of decisions based around it. Like going to a doctor, they're not gonna give you a medical degree when they try to teach you about what disease is happening to you or a family member. They're going to explain all the things they need to explain in order for you to be able to make a decision. And their explanations might not be perfect. And that's okay. Head Start 45, Sad Moody, in your opinion, what improvements can be made to science communication and education of legislators? Thank you. That's such a good question, Head Start 45. Is try to think of a story. Every time you're going to be presenting something, think, what is the story I'm trying to tell? What emotions do I want people to feel when I'm presenting? And what lessons do I want them to take home with me? Even if what you're doing is absolutely technical, but you know that there's going to be people around who aren't, weave a narrative in there. People remember stories, they might not remember details. And having a story as sort of a mnemonic device through what you're saying will just make you way better as a communicator. That's the biggest piece of advice I could probably give anyone. But I try to always think of what's the story in whatever it is that I'm trying to communicate. Is this the stream you put thousands of people in a row? Lucky number 7. Yeah. So we did run over like 450 grandmas. I think our in simulation, we didn't line up anyone, but like we had. I'm not sure if you saw in that slide, but there was like a Baby Yoda death counter and a grandma counter, and a lot of grandmas and Baby Yodas had to suffer for that visual that you saw. But I guess their sacrifice was not in vain. I feel like it was a successful presentation. Questions. In an autonomous crash, who is to blame if the driver is not in control? But the manufacturer, the developer, seems like a legal nightmare. Yes, these are things that are great to discuss. That's a fantastic question, Boltio. I can tell you what's currently happening. So the way that we deal with it, or the way that most companies, I think most autonomous vehicle companies are handling it, is that when we say we've made a level 4 vehicle, we prescribe the operational parameters that need to be around the vehicle in order for our vehicle to be considered safe. So if the vehicle is involved in an accident and it's outside and it's being operated outside the operational parameters that we've outlined as manufacturers, then it's the operator's fault. So the operator would be whoever is deciding to run the vehicles on that particular day. However, if something goes wrong with the vehicle and everything's being followed as we said, then it would be the manufacturer who's at fault. For us, it's a lot easier because we're the manufacturers and the developers for everything. On a scale from Hansen to NWA, how explicit do you rate your code? Hansen to NWA, it's like my code personally is just bodged together. It's been like I've just been a little bit more removed from the actual coding of stuff, and me streaming on Twitch is me trying to get back into getting my hands dirty. But as far as what we do as a company, our code uses lots of different types of components. So rather than, when I said our vehicle is model driven, that's just the drive controller. We actually have a distributed control system for our vehicle. So each there's a component that takes care of each individual function. So like the emergency brake, for example, rather than saying we want a giant operating system that checks whether or not you've pressed the button, no, we'd like to rely on electrical relays to make the emergency stop button. The less abstracted you are from like hard voltages on a line, the more reliable your system goes. However, you can't really program with like just electricity on going through a relay or a wire, a full like complex computer vision system. So we use as least complicated of a system as we can get away with for each individual function that we can think of. And everything communicates in a network. So there's APIs between everything, and we can abstract things away. Hopefully that answers that question. And last question, I think, from Tardy Gravy. So we're one variable change away from robot war. Nice. Yeah, I guess so, but that's true for everything. And if you've got a pace, like a pacemaker, you're one variable change away from that thing shocking you until you die. So yeah, a lot of the time you are one variable. You're one variable change away from losing all your money in a bank transaction. Like it's gonna, yeah. There's a lot of that brings up the need for redundancy. So you have lots of different checks and balances on the way to make sure that if one aspect or one component of your system fails, another one can pick up that failure. So I think search the Swiss cheese model if you're curious. But all right, that's been my talk. I've been sadmoody. Thank you so much for listening. I'm so happy to be part of this conference. Enjoy the after party. Take it away, Fritz.